Hello students, let us start our discussion about magnetic flux. What is magnetic flux? The number of magnetic field lines passes through normal area. Suppose that we have a normal area. Suppose that this is a disk whose normal area is lying just along perpendicular to the plane of this disk, and the total area of this disk is S, and the perpendicular direction of this plane is represented by a letter N cap. Then if there is a uniform magnetic field in which this disk was present, so what will be the total number of magnetic field lines passes through this area of the disk? This can be provided by a term that is known as magnetic flux. So if we take a direction of the magnetic field in this line, along this line, and the angle of the area vector of this disk to the magnetic field is theta, then the number of the magnetic field lines passes through this disk can be given by a simple formula that is known as B dot ds, integration of the B dot ds, where ds is the small area element. So if we take the integration, then we get what? This is equal to integration B dot ds cos of theta. So if B is uniform, then B can be taken outside. Cos of theta is also constant, this can be taken outside. So integration of ds, this becomes the total area of the disk, that is S. So this becomes Bs cos of theta. So this is the total number of the magnetic field lines passes through this disk normally, and this total number can be defined by a small term that is known as magnetic flux. So the total magnetic flux passing through the given area normally can be defined as phi equal to integration of B dot ds. This phi can be expressed by a name that is known as magnetic flux. So what is the unit of magnetic flux? What are the dimensions of the magnetic flux? This can be easily seen from here. The unit of the magnetic flux, there are two different units. First, Weber. This is the SI unit of the magnetic flux. This is SI unit. This is also equal to Tesla meter square. You are seeing that in the formula phi is equal to Bs cos of theta, because we know that cos theta have no any unit. S is the area, it means the unit of S is meter square, and magnetic field intensity B have a unit Tesla, so the unit of this phi is equal to Tesla meter square. So this Weber can be replaced by a unit Tesla meter square. These are same. And the second unit of this magnetic flux is Maxwell. This is CGS unit. This is CGS unit, CGS system unit. And if we relate 1 Tesla, then we get 1 Maxwell is equal to 10 to power minus 8 Weber. This is a simple relation between the SI unit and the CGS unit of the magnetic flux. Now let us come to calculate what will be the dimension of the magnetic flux. Dimension of magnetic flux. So dimension of magnetic flux, from here we are seeing that phi equal to b as cos of theta. Since phi equal to b as cos of theta, and this b can be replaced by a formula. As we know that the force experiencing by a charged particle moving with velocity v in a uniform magnetic field B, that is equal to qvb. So from here b can be represented by f by qb. So from here we can easily get what will be the value of the dimension of this b. So this can be written in terms of bf divided by q into v into s cos of theta. So dimension of f, dimension of phi is equal to dimension of f, that is mlt power minus 2, and dimension of q, that is ampere second at, and dimension of v, that is velocity lt power minus 1, and s, that is meter square, and dimension of cos theta is nothing. So from here we get the dimension of phi is equal to m l, this l and this l will be cancel each other. From here l square and this t and t will be cancel each other, and from here t power minus 2 and a power minus 1. This is a simple dimensional formula of the magnetic flux. So let us define what is the magnetic flux. Magnetic flux is the number of magnetic field lines passing through any area, any given area normally. Suppose that if we take this area as unit, if we assume that the magnitude of this area is unit, so if we take this as equal to 1, then also if we assume that the area of this plane is just perpendicular or parallel, or this plane of this area, plane of this plate or disc is just perpendicular to the magnetic field, it means the area vector of this disc is just along the magnetic field. It means cos theta is equal to cos 0, that is 1. So from here we get phi equal to b. If we take what, s equal to 1 meter square and theta equal to 0, then we get phi equal to b. So we can easily define the magnetic flux in different terms. Magnetic flux is just equivalent to the magnetic field intensity or the strength of the magnetic field when any plate or any area element can be placed perpendicularly to the magnetic field, and the plate or the material contains unit area. Okay, so magnetic flux passing through any unit area element is equal to the magnetic field intensity, which is placed just parallel to the magnetic field. It means the area vector of the magnetic the area vector of the disc is placed just parallel to the magnetic field. It means the plane of this disc is placed perpendicular to the magnetic field. So this is a simple concept by which we can define the magnetic flux. So this is the magnetic flux, and this is the unit of magnetic flux, and this one is the dimension of the magnetic flux. Now let us come to the next topic, that is known as Gauss law for magnetism. So let us come to our next topic, Gauss law for magnetism. As we know that Gauss provides a similar law for electrostatic, and in that case we have stated that the total electric flux passing through any closed surface is equal to the 1 upon epsilon naught times the net charge bounded by that surface. It means, suppose that we have an enclosed surface, and this enclosed surface encloses some charge within it. Then due to this charge there are different electric field lines emerging out or entering it. if the charge nature is positive, then emerging out. If the total charge nature is negative, then entering in it. So the total number of electric field lines entering perpendicularly to the surface is known as the electric flux, and Gauss law provides the electric flux passing through any enclosed surface is always equal to 1 upon epsilon naught times the Q net enclosures inside the surface. This is a simple law. This law is given by Gauss for electrostatic. Now Gauss also provides a simple law for magnetism. In magnetism, he provides the calculation of the magnetic flux passing through any closed surface. Suppose that we have a closed surface and we encloses some magnetic substance. Suppose that here is a magnetic substance. As we know that magnet is always present with dipole. The monopole of the magnet cannot be exist separately. So if there is a north pole, then there will be also the south pole. If there is a dipole present in this closed surface, then the total number of magnetic field lines emerging out from this north pole will be equal to the total number of magnetic field line entering to this pole on the magnet south pole. So if we calculate the total number of magnetic field lines emerging out or entering into the surface, then we get this will always be equal to 0. So we can easily say that if we assume that there is a bar magnet N and S, and there is a different magnetic field lines entering from the S pole and leaving from N pole. Okay, so we can easily see that if we choose different area element, suppose that if we take a small area element at here, then the total number of magnetic field line entering in it is equal to total number of magnetic field line leaving the surface. So we can say that the net magnetic flux passing through this surface is always equal to 0. So if we apply the same condition, it means phi net is always equal to 0. And as we know that the definition of this phi net can be written as integration of the B dot ds. Suppose that this small area element is ds, the integration of B dot ds is always equal to 0. This is the statement of the Gauss law for magnetism. Okay, with the help of Gauss magnetism, we can easily say that, or we can conclude that the existence of monopole is impossible, and there is no any method to separate the single pole of a bar magnet. Because when we break the bar magnet into two or more different pieces, then each piece contains the south and north pole. It means each piece becomes a magnetic dipole, and we cannot find out the separate pole of the magnet. So with the help of this, we can easily find out the total magnetic flux passing through any closed surface is always equal to 0. So this is the statement of the Gauss law for magnetism. Okay, so in our next lecture we have seen that the different applications of Gauss law for magnetism, and also we have seen that what is the earth magnetism, what is the dynamo effect, what is dip, what is inclination, and what is declination. So we will see it all in our tomorrow's lecture. Till now, take care. Thank you.